Alright guys, welcome to Earth. This is Thursday, June 7th, 10:50 in the morning, Pacific time. This is Cory Andrew Hofstad, and basically today we're going to give you a quick breakdown of electroacoustic propulsion systems and the wave-assisted propulsion system testing and research environment being developed here at North Seattle College through independent study. Let's get this started. So again, this is wave-assisted propulsion systems. It's an engineering platform that I'm putting together. Basically what we're doing is, I don't know if there's a lot of videos on YouTube. There's cymatics by Hans Jenny. There's also cymatic soundscapes. There's cymatic videos by Nigel Stanford, which you can look up. And basically what it does is it shows that matter and liquids and gases and even solids are moved by sound. You can vibrate your car with a loud subwoofer. You can vibrate water. You can vibrate a cloud of gas. And what that is motion. Fast-moving motion, oscillation is what we call it in science. And so what we're doing with this is this experiment, which is an independent study in North Seattle College again. What we're doing with this experiment is we are creating a rotational column in a propellant cloud, which is going to be used for ionizing and exhaust in electronic propulsion systems. We're attaining a rotational pattern in that cloud, which can be used with Maxwell's corkscrew and Coulomb's force for the rotational movement of a particle in a magnetic field. And if we get that rotation going, it moves a lot faster than trying to accelerate a particle from rest. And so basically we're just trying to get this stuff moving with sound in a rotation that matches Maxwell's corkscrew when we eject it with a magnetic field. And so let's get this started. First, we're going to talk about the methods of current electronic propulsion systems. This involves propulsion system housing, which would contain the gases and all the parts of a system. I can provide some links for you guys to look up some of the common methods. I have an article from Princeton I think I'll attach here. Noble gas propellant, for example xenon, other halogens work. Basically what it is non-corrosive, and it's easily ionizable. You don't want to corrode the inside of the thruster housing when you're at long space missions. You don't want it to destroy anything. You don't want it to pull anything apart. You don't want it to create bonds, basically. And then a magnetic field, which is used to ionize the propellant. Basically, then you have a magnetic cloud, and with like any other like ferrofluid or magnetic powder or iron flake or anything like that, a gas cloud is going to be the same thing, where it's going to be attracted or repulsed by a magnetic field. So you can move it around, you can shape it, you can have it gravitate to an area, you can propel it out to create thrust. And in this case, in thrusters, that's exactly what we're doing. In the case of a magnetic grating, the cloud is going to be attracted and then repelled by the negative and the positive fields, which are created by the grating, which would be two gratings with different magnetic fields. And as it's attracted and then repulsed, it comes out at a very high velocity. Also, coaxial exhaust nozzles are used for the same reason, using Coulomb's force and Maxwell's corkscrew effect, which allow a rotational exhaust formation to come out and propel the ship. Like I said, the ionized gas through a grating or a nozzle mechanism is going to be exhausted, and it's going to come out the other end. And it doesn't need to be a lot of thrust in space, because basically when you're at space for say a month at a time and you have a low amount of thrust, it's going to add up, and so that acceleration is going to add up to very high speeds. When you're at space for a year or more, or interstellar missions, which we're planning on for the future, or just going to Mars, 6 months to a year, those velocities with no or a little friction in space, whatever you bump into, you can get going pretty fast with an electronic propulsion system. Rockets are great for getting off of space. If we're going to talk about rockets real quick while we're doing this. So rockets, basically it's a chemical combustion reaction, like an oxidation reaction with an ignition, which creates a very large amount of work, which is exhausted out the nozzle. It releases a lot of heat, which isn't necessarily a good thing, because you want to try to keep that heat as energy. And it just creates a lot of thrust, and it's directed in a perpendicular to the ship, and then you get movement. That's kind of similar to electrothermal devices, which create thrust and electronic propulsion systems by expanding propellant gases with heating elements. And so what that does is gases, the natural gas law, PV equals nRT. When you raise the temperature, it's going to raise the pressure and the volume, or both, or whatever is allowed inside of the system that we're using. In a rocket, it would be temperature, and it would be pressure, and the volume would exceed out the exhaust nozzle, creating thrust. And so that's another method that is used in electronic propulsion systems currently. And so these systems are used in space. Let's see. Basically, I'm just going to give you a quick overview of electronic propulsion systems so you guys can see what exactly we're talking about before we go any further.
Mark Millis ran NASA's Breakthrough Propulsion Project. One of its long-term goals was to move away from using rockets. The problem with rockets is not that they can't beat gravity, it's the amount of thrust they need to do it.
If you think about the Apollo spacecraft, and you imagine here's a Saturn V, the very tip of that and then a little bit below that was the actual spacecraft itself, and all the rest of this was the propellant with the rocket fuel, and that's just to the moon.
At the Glenn Research Laboratory in Ohio, work is underway to produce new forms of space engines. Ones that really could take us where rockets can't, beyond our solar system.
What we have here is a high-powered ion thruster, and the way it produces thrust, our ions are created inside this ring, and then we establish electrostatic potential that accelerates these ions out and produces large velocities. And what that does is it gives us very efficient production of thrust.
This is an ion thruster under test, pouring out a constant stream of charged particles. It's less powerful than a rocket, but capable of accelerating a spacecraft almost indefinitely.
These systems are ideal for in space. We operate them purely in space because it's very gentle. The thrust level is low, but over time you can develop much higher velocities than you can with chemical rockets.
All right, and so those kind of devices, and that's what we're dealing with. I just wanted to show you guys that before to give you guys like something real to see before we go into some of the theory stuff. So next, right, we're going to give you some of the methods for our wave-assisted propulsion system Mark I, the Electroacoustic Propulsion Thruster. I have some pictures here that I can throw in here, and also some links so you guys can see a little bit more about that on GitHub and such. Basically, I'm going to give you a brief overview of how this system works. And so we would start out with a traditional propulsion system housing. There's many designs. We have a very simple cylindrical design. It's just for testing purposes right now. We're going to make some different sizes and some different configurations. I'm going to send you guys a link for Kickstarter so we can get some funds together to get some of those parts and get some more acrylic and some more wave drivers and some more equipment. It still uses a noble gas propellant, for example, like xenon. We're going to use xenon for one of our final stages in testing when we're actually at the propulsion and ionization stage. First, we're going to use Lycopodium for its resemblance of gas, and then we're going to use SF6, which is sulfur hexafluoride, which is a heavy gas like xenon, a heavy gas that we can use, like, say, for like miniature ping pong balls, right? We put that on top of the heavy gas and they'll float, and then we can oscillate it and we can watch the movement. The movement is going to be created by an embedded wave driver system. And what that embedded wave driver system is going to do is it's going to take a random gas cloud that is basically with no formation, with just kind of floating around randomly, and it's going to put a formation in there that we're going to test out. We're going to look at different formations in SF6 and Lycopodium, and so we're going to find which frequencies generate the best rotational formations, and we're going to fine-tune those for xenon, and then we're going to use those eventually on xenon with an ionization, electrical energy to charge it, and what that is right here. And so what we can do is we can get a rotational cloud of xenon going in a tight formation, and then we can ionize that cloud of xenon. When we ionize that cloud of xenon, then at that point we have what you would call a plasma vortex. And that plasma vortex is going to contain a lot of kinetic energy, a lot of ionized energy, a lot of movement, and a lot of charge. That's a lot of energy which we can use for propulsion techniques. Our current system plans on using a coaxial exhaust nozzle. Basically, we're just using that just because Maxwell's corkscrew and the right-hand law of electromagnetic wave and particle transfer shows that particles, when traveling in a magnetic wave, are going to take a rotational pattern. They're not going to move straight. They're going to move in a rotational pattern, like a sine wave or any other wave. They move in a wave, and so when we have a rotational pattern, it's created by our sound wave and our cloud, and then we have a coaxial, which we're trying to eject the cloud down. We started with just at-rest particles and at-rest cloud. that magnetic field has to pull them into a rotation and eject it. What we're doing is we are getting the cloud moving and then just shooting them down the tunnel, and we're going to create a lot of velocity. And I'm going to show that in my next slide. The ionized gas is going to be ejected through the exhaust column and accelerated velocity, creating a dense exhaust cloud. This is going to be used to create higher exhaust velocities in space travel, extending our fuel, because instead of using all our electromagnetic energy to accelerate a cloud from rest and using a lot of energy just to get it going, if we have if we can get better solar panels, or like say some kind of reactor in space, we just use that energy to make the cloud have a high velocity of rotation within the thruster column, and then when we go to eject it, it's going to come out a lot faster using the same amount of chemical fuel. And so that means all we have to do is just hunt for electricity in space, and our chemical fuel supplies they're going to last a lot longer, and we can get around a lot faster with higher velocities using sound. This is a great thing. So, like I said, the propellant plasma rotation is ejected along the cathode following Maxwell's corkscrew with an accelerated velocity from oscillation of molecular particles. And so that's basically what I'm talking about, is everything's going to be accelerated because the cloud is not at rest anymore. Here's a diagram I put together of how do vortex formations affect particle velocity in electronic propulsion devices. Traditional electronic propulsion systems accelerate particles from rest through a coaxial system or electromagnetic field which follows Maxwell's corkscrew. Since these particles move from rest, Newton's first law, says an object in motion is going to stay in motion unless a force is applied, and a lot of that force is going to go into getting it to move. And so in wave-assisted propulsion systems, they accelerate the particles with a rotational velocity, using Maxwell's corkscrew to increase the velocity. So we're not accelerating it from rest, we're just increasing the velocity, which means that since the velocity is increasing, not from rest, it's already going to come out. That's like you have a drag race, right? And when he starts from zero, and you get to start at the end of the, it's far back, and he only gets to start when you pass the start line. And so you're coming across the line maybe at a 60 miles an hour, and he's coming across at zero. And so whoever finishes at that quarter mile, it's probably going to be the guy who comes across the starting line or already moving. And so this is a little diagram just so you guys can see how that works. It's all about Newton's first law and not having our gas particles at rest. That's what this whole experiment's about. We don't like gas particles that don't do anything. Some more theories that we have that we're putting together based on this idea. I don't have any equipment. I don't have the equipment purchased or planned for this lab. It's another theory that could be used possibly in atmosphere. It would be a propulsion system housing. It would be like a cup or a bowl that would be upside down with the opening there on the bottom, and the rest of it is like a container, a vessel. And there would be a noble gas propellant, and in this case, since we're in atmosphere and we want it to stay in there and not escape from the bottom, we're going to use helium, which is lighter than air, so it would stay up in this little bowl. We would then use an electromagnetic field to ionize that propellant or that helium, creating the same effect as xenon or any other ionized gas cloud. We would then use a magnetic grating on the bottom to create like a traditional like ion thruster type assembly, except for instead of using the coaxial, we're going to use a magnetic grating. What we'd do is we'd use an embedded wave driver, which would create a high velocity turbine of gas, of helium gas, which would go in a rotational formation, which could be used to create another corkscrew effect. The helium vortex formation acts as a rotating turbine, providing exhaust power in the form of air pressure. Thrusters could be used in synchronous formations, allowing for large volumes of thrust over great areas. And so we could create a lot of thrust using helium as a turbine mechanism, using this theory of sound and electroacoustic propulsion. So how could helium vortex formation work as a turbine propulsion system? So vortex formations have a draw, an inlet and an outlet. Just like in hurricanes, tornadoes, or like in water pools, there's always some kind of suction that it comes from the corkscrew effect and the Maxwell's corkscrew effect. When there's a spin, there's some kind of draw, some kind of almost like an electric charge. Bang! There's science. Alright guys, so for anybody at NASA, the ESA, JAXA, the Russian cosmonauts, anybody, any of the private companies, Boeing, Lockheed, SpaceX, Northrop, all you guys, anybody who wants to jump on this technology now is a great time. Electroacoustic propulsion, it's going to save your chemical fuel. It's going to save your bottom dollar, and it's going to get you further. We're going to get out of the Milky Way galaxy using this, like I said. So here's some links at the bottom that you guys can check me out. First of all, check out my GitHub. It's a great place to find my data and my notes and my technical documents and my ideas, all published under open source, MIT license or unlicensed, or the GNU lesser general public license. Check me out on ResearchGate, man. You can check some of my articles and my journals. You can comment and you can share them and you can critique them. If you find something wrong or you want to fix or have me fix or anything, just let me know on ResearchGate. I'll get back at you as soon as possible. For some of my larger files, you can check out my repositories on the Harvard Dataverse. I'll send some links on the bottom right here. And also the Open Science Foundation, my electroacoustic propulsion project. My videos and my big files are going to be on those guys. Check me out on Facebook. Check me out on Twitter. Check me out on YouTube, definitely. I got good videos there. You can see visually what we're doing. It gives you a better description of what's going on. Check me out on GoFundMe and Kickstarter. I definitely need some donations, definitely need some funds to get some of this going. It's kind of expensive for hardware, making trips to Fry's, ordering stuff on Amazon, ordering stuff through these different scientific companies. Check out some of these other scientific funding websites. We're looking also for gifts of kind. And so here on the bottom, I'm going to include my address. You can send me packages there. Here's my email also with my phone number. Basically, we're looking for like audio equipment, amplifiers, power supplies, decibel meters, measuring equipment, lasers, mirrors. If you can get your hands on some xenon and send that my way, I'd be appreciated. Sulfur hexafluoride also, SF6, it's very expensive. Lycopodium even. Acrylic. If anybody wants to order me some acrylic, the tubing for this project is really expensive. We could definitely use some of that. It's about like $100 a foot. Some of the smaller sizes are cheaper. Jump on board, man, with this. We're trying to save chemical fuel out there and get to where we need to go in space. I really appreciate everything you guys have done so far. Watching my video, this has been great. This is my first presentation. I'm really proud of everybody who's taken a part of the project, my teachers, the administration, everybody. I got some more work to do. I actually got to go to the electronics store and pick up some parts. So we're going to call that a finish. And thank you guys. God bless.